Okay, all right. Well, good morning. And we'll take a look at today's lecture. And again, this would be considered bonus content, not going to be put on the final exam here. So yes, last lecture, I guess, to be on the final would be week 9, Friday. Okay, but oh, these are both, everything looks terrible. Give me a second here. Okay, all right. Something. Screen share is, how do I resume screen sharing? Share. Resume. Okay. All right. I hope this works. All right. So in our last meeting, we talked about decision trees, and we said, we partition our data into these different things, and decision trees are great. However, decision trees are very limited because especially in the case of like regression, okay, as far as making a numeric prediction, you can only have as many numeric predictions as you have final terminal nodes. So you might have, for like the cars data set where we're trying to predict the price of a car, you might split on a couple different variables, and you might have, say, 8 terminal nodes, right? So if you split on one variable and then do another split and another split and so on and so forth, you might end up with 8 terminal nodes, which means you can only predict 8 different prices of vehicle. So you can say, all right, this car we predict is $10,000, and this one is 11, and this one's 12,500, but you can only have 8 unique values. And clearly you probably need more than 8 unique values. So, how do we improve the prediction ability of a decision tree? Okay. And the answer is basically more trees. Okay. And so we're going to look at a couple methods that will improve the predictive performance of trees. Okay. So the trade-off, however, is that now things get more complicated and it's a lot harder to explain or describe. So with the decision tree, it's very simple. You just say, hey, go down this path or go down that path. And it's very easy, but these methods, basically we have more trees. So the first kind of method, or I guess part of it, is called bagging. Okay, bagging is basically we are applying bootstrap to a decision tree. We don't generally do bagging by itself. Bagging is part of the random forest, but I should explain what bagging is first, okay? And so the idea is you do this bootstrap resampling of the training data. So remember, with bootstrap resampling is you take your available data and you pretend it's your population by kind of making infinitely many copies of it or sampling with replacement. And so you resample your data and you get, another sample that is similar but a little bit different from your current samples, right? Your bootstrap resamples, you're resampling your data with replacement. And then so after you resample your data, you fit a decision tree to that, okay? And so the resulting decision tree is going to be a little bit different from your original decision tree. So you have your original decision tree based on your original data, then you resample your data, you get a slightly different looking data set, and you fit a decision tree there. And you create a whole bunch of these decision trees. And then when it's time to make a prediction for a new observation, you feed that prediction through all of the different trees that were created in this process. Each of them makes a slightly different prediction. And based on your slightly different predictions, you take the average of all of them, and that will be your final prediction, okay? So you run your test observation through all of the created decision trees, average their predicted values, or if you're doing classification, do majority vote, and that's what we do. So just to illustrate this, we'll take our toy example, where we basically just have 5 unique values of X, and we're going to just create these tiny little decision trees. So if you recall our first decision tree, we made a split between the third and the fourth observation, where values where X was 3 or less, we would predict like 1.67, and then values where X was 3.5 or higher, we predicted 7.5. That was kind of our first decision tree. But what we'll do in here is we do a bootstrap resample. And so with my bootstrap resample, I take my original data and I sample with replacement. I end up selecting the fourth observation twice. I never selected the first observation. And so now here is my my data, and I say, all right, let's go ahead and fit a decision tree here. And so for this decision tree, probably I'll also do a split between X is 3 and X is 4, okay? However, my prediction for when X is less than 3, I'm going to predict probably the average of Y, 1 and 3, so I'll predict 2, and I'll predict the average of 7, 7, and 8, so what, 7.33? So yeah, if I say our part, create a decision tree on this, my split happens, as I anticipated, between 3 and 4, and the prediction is going to be 2 or 7.33. So that's when you resample your data, that's what we get that, for this one, okay? Here I do another bootstrap resample. This time, when I resampled my data, I ended up selecting observation 3 twice, okay? And so I'm going to make a decision tree here. And so for this decision tree, I end up creating the split at the same location as before between X is 3 and X is 4. So we're going to have the kind of the same split there. However, my predictions are going to be, 7.5 here, and the average of 1, 3, and 3. My prediction is going to be 2.33. Okay, so I'm making slightly different predictions, even though I have the same, I'm using the same kind of border at, X is 3.5. Okay, and then I'll just do one more example. And in this example, I just happen to, by coincidence, select row 1 3 times and row 4 twice. Okay, so even though I had 5 observations of my population, when I resampled it, I ended up, this is my data set. Okay, so I'm going to draw a split between X is 1 and X is 4. So the average would be like 2.5. Okay, so I'll just draw a split there at 2.5. If my X value is less than 2.5, I'm going to predict Y is 1. And if X is greater than 2.5, I'm going to predict Y is 7. Okay, and so that is, those are my 3 trees. Okay, so So let's say we have a new test case, all right, and I'm going to say my new test case has x equal to 4. So what is the prediction I'm going to end up making? Well, I feed it through all 3 of my trees. So the first tree, if x is 4, I'm going to go down this branch or this node, and I'm going to predict 7.33. For the second tree, if x is 4, I'm going to predict 7.5. And for this tree, if x is 4, which is greater than 2.5, I'm going to predict 7. So my predictions are 7.3, 7.5, and 7. And if I take the average of these 3 trees, I get 7.278. And that is how we do bagging, okay? So bagging is we take our data, resample it, fit a tree, do it a bunch of times, and when it comes time to make a prediction, we feed that same new test case through all of them and take the average, okay? Again, we generally don't use bagging all by itself. And bagging is usually one part of the random forest procedure, okay? So bagging randomizes the observations used in the training data, but then what random forest does is it randomizes the variables that we can use when creating a tree. Bagging alone is not recommended because it tends to produce overly correlated trees. So when you fit trees that are bootstrapped samples of the data, then pretty much almost all of the trees that you create will be very, very similar to each other, which can end up leading to overfitting. Basically, any kind of unusual features that are present in your training data set can end up being part of the model, even if they're not something that generalizes to the population or the real world. And then the other issue with bagging is that certain variables can be so strongly correlated or such a good predictor for the response variable that you become like overly dependent upon it, okay? So because this predictor is so good, you could end up with pretty much all of these trees using that same variable for the initial split, right? So all of your models are dependent upon this one variable. And so it's going to have poor predictive performance if you happen to get a test case where that one, that primary variable doesn't do a good job, okay? Or if it's like an exception to that case, okay? So to avoid this problem of trees that are, too similar, okay, or overly correlated, what random forest does is it introduces random selection of variables. And so as far as the individual tree goes, the individual tree is, quote, impaired in that they will be restricted from using all of the variables available in the data set, okay? The individual tree, each individual tree has to kind of, come up with like I mean, there's no creativity involved, but basically you're saying, you're telling a tree, do your best job of predicting our outcome variable using only this subset of variables, okay? And you kind of constrain each of these individual trees in that way. So none of the individual trees are going to be optimal, okay? But you're going to have a whole bunch of these optimal, suboptimal trees, but they're also going to be very diverse. Okay, they'll also be very different from one another because this tree was restricted to this subset of variables. This other tree was restricted to a different subset of variables. And thus you'll get, by incorporating all of these different trees, overall, you'll be using pretty much like all of the different variables as far as making your prediction goes, okay? Whereas when you didn't have this random selection or subsetting of variables, even if you did bagging 100 times, you might end up using the same 5 variables every single time, Okay. And if you have a kind of a big data set with, say, like 40 variables, sure, the other 35 variables might not do as good of a job predicting the response, but with random forest, you know, by implementing this uh, restriction, you're going to probably end up using all 40 variables, okay? Some of those trees will be suboptimal because they've been restricted to using, these 5 variables that aren't very good. But they did their absolute best that they could with those, 5 not so good variables, okay? But if you take all of them into account, now you have basically a model that uses all 40 of the variables rather than just using the same 5 variables over and over again. Okay, so yeah, the hope is that by having many suboptimal yet highly diverse trees, the resulting prediction made by the aggregate of all the trees will be better. Okay, the silly analogy is like you're trying to put together a superhero team like the Avengers or something. Okay, and if all 5 of your superheroes are like basically the same superhero, it's not, with all of the same strengths and weaknesses, right? Like if the Avengers were just 5 copies of Iron Man, um, you would run into like, I don't know, if there was some kind of issue or whatever that, that particular hero or whatever wasn't well suited to solve, then you know, it it's I guess it's not as good, right? And the power, these kind of ensemble teams is that each one has their own kind of unique ability, right? And you could even say incorporate, say like Daredevil, who is, a blind superhero. And that superhero can help out in situations where vision is not useful or something, right? Like if you end up in a dark cave or something like that. Okay. And so if you end up in a scenario where some of your predictor variables are either missing or, um, just very different, can you still make a prediction or something like that? With random forest, you might be able to. Okay. And so when we do random forest, the process looks kind of like this. You're going to do a bootstrap resample of your training data. So that's kind of the bagging part. But then when it comes to fitting the tree, you do a random subset of the variables. So, your original data set might have 40 variables, and you might restrict this tree and just say, you're only allowed to use these 10 variables, okay? And it has to do its best job of creating a good decision tree using that subset of variables. And you're going to do this a whole bunch of times. Each tree will have a different random subset of predictor variables and a different random subset of the training data. And so you'll have this kind of a bunch of different trees. That's where the forest part comes in. And the random part is, the random selection of variables. So that's the random forest. And then when it comes time to make a prediction, you average all of the predictions. Okay, so we have this little diagram here. And this would be a classification one, but regression, you would just take the average of all of these things. But basically you create, here's one tree and it has some variables. Here's another tree with different variables. Here's tree number N with other variables. You feed your prediction, your new test case through each of these trees, and they make either, different predictions or, they make different predictions, whether it's predicting a class or predicting a value. And if it's a class, you do majority voting. If it's predicting a value, you take the average of all of them. And so that's random forest. So here's an example that we can do in R. There's a library called Random Forest. There's another library called Ranger, which probably actually has better performance. Ranger is, I guess, a play on words with, you have a forest ranger type of thing. And And so that would be the package that I guess handles the forest. But here we're going to take a look at this air quality data set. And so the air quality data set, keeps track of a bunch of different, I don't know, I guess, pollutants and things in the air. And one thing that we might be interested in is a ground level ozone. So I don't know if you were ever when I was younger, there was a lot of concern about the ozone layer, and I don't know if you've heard of this thing. And basically, ozone's this, I think, O3 molecule, and in the some of it exists in the atmosphere, and it protects us from, I guess, harmful radiation and whatnot. And there was a problem with the ozone layer over the I think Antarctica because of different chemicals and stuff. And so they I think, was it the Montreal Treaty or something? They banned these chemicals around the globe, and then it fixed the problem. And so the ozone layer is no longer a problem. So the ozone's an important thing in our atmosphere to protect us, but on the ground level, okay, ozone's not good for you to be breathing in as a human. So like we want regular O2 oxygen, O3 ozone is bad for people. And so it is considered a pollutant kind of at, ground at the surface level. It's a good thing to have in the atmosphere. We want to make sure it's still around. We don't want to be breathing it in. But anyway, we can say, all right, go ahead and create a random forest to predict kind of ozone content. And I just did kind of the laziest formula, which is predict ozone based on all other variables available in the data set. Just the tilde dot is use all of the other variables here. But then a random forest is going to automatically create subsets of all of the different variables available. And so you have this mtry. Mtry says, anytime you make a tree, try out, just select 3 variables, okay? So this is a small number, but yeah, 3 is fine, okay? And then we could just put in these other things. Na.omit, na action, na omit is just says, hey, if something's missing some values, then just don't include it in your prediction process here, okay? And so that's the command to create a random forest. And the default is it's going to make 500 different trees. The number of variables tried at each split is going to be 3 variables. And at the end, it says it was able to explain, around 72% of your variance. So this is, akin, similar to like an R-squared value. Obviously, we want to do something a little bit more robust than R-squared, which is if you use this as your only guiding principle, you're prone to overfit, but we can do something like that. And so here, if we take a look at our first observation, I guess our variables to predict ozone, we have solar R, wind, temperature, month, day, and when we make a prediction, we predicted 35.9588, okay? And so we can see, how different we are, and that's how random forest works, okay? I'm a big fan of tidy models, and so, if you're going to fit a whole bunch of models, I recommend checking out the Tidy Models package. I covered in my 101C class, but if you're, I don't know when the next time I'll teach it actually is, but but if you are looking to fit like statistical models, look up Tidy Models. There's free textbooks and a lot of good resources for using it. Okay, and then the other method that incorporates decision trees to improve performance is boosting. Okay, and so one of the most popular, or another very popular kind of machine learning package is called XGBoost, Extreme Gradient Boosting, and it is it basically uses boosting, and then the XG part is like how it kind of fits fits all of these things together, like did the computational aspect. Okay. But boosting is consists of creating a whole bunch of tiny, like very weak trees, but you're going to create like a ton of these things. You're going to fit the trees to the residuals. So you fit this terrible tree, it makes predictions, and then you calculate the residuals to see like how far off you are, like how far, like how much error there is in your current model, and then you fit another tree to these residuals, and you keep doing that to kind of refine your model. You also include something called the learning rate, and this slows down the learning here. Okay, so so anyway, the way it works is your initial guess is you're going to just predict the mean for everybody, and then you calculate all of these residuals, and you're going to fit a decision tree to those residuals. And however, when you do that, rather than updating your prediction with what the decision tree tells you to do, you temper it by multiplying it by a learning rate. A learning rate says, you know, basically only take into adjust your thing by 1% or something like that, right? So let's say, you know, you calculate your residuals, and based on the tree, it says, okay, we need to move to the right, or you need to move to the left. And it says, okay, how far should I move to the right? And it says, okay, turn 30 degrees to the right. And what the learning rate does says, okay, I will just take that into account, like 1%. And so rather than turning 30 degrees to the right, you turn like 1/3 of a degree to the right. Okay, so you just turn just a tiny bit to the right. Okay, this is, so we call this a slow learner. Okay, so boosting learns slowly. We fit these small trees, low variance, high bias trees, and it trains on the errors. Okay, each iteration learns to predict the mistakes of the previous iteration. This idea of slow learning and using kind of this learning rate is, I like to think of this as like adjusting the temperature in your shower. Okay, so let's say you're in the shower and you say, okay, well, I would like it a little bit hotter. Okay, and there's a couple like methods you can try this. Is you could turn the temperature knob so it goes hotter, but a lot of times, you know, you change the temperature and then it's like too hot, so then you have to move it back, and then you go, oh no, now it's too cold, and there's kind of this back and forth um you know, sequence there. Okay, boosting tries to avoid that by saying, okay, I want the temperature higher, and so I want to adjust the temperature to be higher, but basically it just taps the temperature handle just a tiny bit. Okay, and then so it barely makes any change, but you go, okay, I still want it a tiny bit higher. So you tap it just another time, and it barely adjusts the temperature. And you keep doing this very slow adjustment, okay, until it kind of finally gets it right. Okay, versus the other of like, oh, it's, you know, I need it hotter, and then you move it to the right, and you go, oh no, it's too hot, and then you move it back, and something like that. So boosting is just at every time kind of opportunity, you just make the smallest adjustment to your prediction, and that's what this lambda does. Okay, so I'm going to we'll walk through the calculations of using boosting here, and uh, and just for the sake of being able to show how the boosting works, I'll use a much larger lambda than typical. The learning rate lambda is usually around something like 1%, but I'm going to use like a 30%. And that's it's still less than 1 and it's still less than a half, but that will show you how it's just adjusting your predictions a little bit. And then I'm going to just fit maybe say like two steps of boosting, okay? Where normally you'll fit thousands of these trees, okay? And so the resulting model is going to be quite terrible, but it'll show you at least kind of how the model makes these predictions. And we'll do it in R as well. So, okay. So again, here's our toy data set with 5 unique values of X, and our values are 1, 1, 3, 7, 8. And so we start off by predicting the mean for everybody, 4, and then we calculate the residuals. So if we predict 4 for everyone, all of my residuals will be, I subtract 4 from the actual values. I get -3, -3, -1, 3, and 4. And now I'm going to fit the tiniest tree to the residuals, okay? These tiny trees, sometimes we call them stumps because there's just going to be one branch, okay? Or one split. And then we make our predictions. And so we're going to split between x's 3 and 4. And if x is over 3.5, we will predict 3.5. And if it's less than 3.5, we will predict the average of this. So -7 divided by 3, so -2.67, okay? Or -2.33, sorry. So these would be the predictions, okay? That's if you predict the residuals directly. So this says 3.5 or -2.33. And currently, our current model predicts 4. And according to this tree here, our next prediction should be 4 plus 3.5 to predict 7.5, or 4 minus 2.33 to predict 1.67. And that would be what we would get if we just used the tree's prediction directly. And we would get pretty much the exact same tree that we had if we just fit a regular tree, right? Because you would predict 7.5 and 1.67 if you do 4 plus whatever these predictions are. Okay. However, we are not going to use these directly. We're going to adjust our prediction by lambda times this. Okay. So if our lambda is 30%, I'm going to do 30% times 3.5. Okay. So if x is greater than 3.5, I would predict 3.5. But rather than doing 4 plus 3.5 and predicting 7.5, I'm going to do 4 plus 0.3 times 3.5. And now I'm going to predict 5.05. Okay. And then rather than predicting 4 minus 2.33 and predicting 1.67, I'm going to do 4 times 0.3 times this. And now my predictions are going to be 3.3. So if x is greater than 3.5, I predict 5.05. If x is less than 3.5, I predict 3.3. Okay. And now I'm going to calculate residuals between what my y is and what my predictions are. So my residuals are -2.3, -2.3, -0.3, 1.95, and 2.95. So I'm going to use this. I'm going to fit another tree to that. So here are the values that I have. I'm going to say, all right, go ahead and fit a tree here. And when I fit a tree, it says split at x above or below 3.5. And if x is below 3.5, predict the average of these, which is -1.63. If x is greater than 3.5, predict the average of these, which is 2.45. Okay. And again, rather than adjusting our predictions by this much, I'm going to temper that with my learning rate. Okay. So right now, so far my predictions are 3.3 over here, and I would adjust it by 30% times -1.63. So now I'm going to predict 2.81. And currently my predictions are 5.05 for over here. And I'm going to multiply that by 30%. It says adjust your prediction by 2.45, but I'm going to adjust it by 30% of that. And so now I'm going to predict 5.785. Okay. I calculate the residuals for all of these predictions. My residuals now are these numbers. And so I have negative 1.81, negative 1.81, 0.19, 1.215, 2.215. And we're going to predict on this. So I have X is this, I'm going to fit a tree here. And I think this time when I fit the tree, it says make the split at 2.5. Okay, so up until now, we've been splitting at 3.5, but now we're going to split between 2.5. If X is less than 2.5, adjust your prediction by negative 1.81. If X is greater than 2.5, adjust your prediction by 1.206, okay? But again, rather than adjusting it directly by negative 1.81, we're going to multiply that by 0.3. So I do, currently my prediction is 2.81. I'm going to adjust it by negative 1.81 times 0.3, and I'm going to predict 2.267. Over here, I predict 2.267. These values over here are greater than 2.5, and it says you should adjust your prediction by 1.206. We're going to multiply that by 0.3. And so now we predict from 2.81 plus 0.3 times 1.206. We predict 3.172. And then for these ones, we predict 6.147. So despite having only small trees and this learning rate, now we have at least 3 unique values that we're predicting, okay? And we would continue this process, hundreds of times, thousands of times. And eventually you end up getting a model that is able to make pretty good predictions, okay? As cumbersome and slow as this is, again, because we have computers that are able to do all of these calculations for us, we are able to fit this boosted tree, okay? And so, it is computationally expensive because it has to fit thousands of these tiny little trees and make small adjustments and incremental changes. But eventually you get some decent predictions. Okay, right now our predictions are terrible. I fit 2 of these trees so far. Okay, so we started off, or was it 3 trees? We started off by predicting 4, and then I think I did just 2 additional trees after that. So these are not great, okay? But this is how the boosting process works. If I use a package in R, so in R, there's a package called GBM that's going to perform boosting. I guess I fit 3 trees. And I can tell this package to use the same terrible conditions that we had, like fit a total of 3 trees and you use a learning rate of 30%, okay? And if we constrain the boosting package to the same conditions that we used, it will end up making the same predictions. So the predictions we made were 2.267, 3.172, and 6.147. And here I'm going to tell it, predict Y based on X, fit a total of 3 trees. Again, normally this is like 1,000. Shrinkage is normally around 1%, but we're giving it the same exact kind of conditions that we used. And when we do that and we say, hey, make a prediction for when X is equal to 1, it predicts 2.267, which is what we have, okay? And we say, hey, make a prediction for when X is 3, and it predicts 3.172, which is what we have when we did it manually. And then lastly, it predicts 6.147. So our results align with what R is producing when we give it the same kind of conditions. And so, that's always at least encouraging as far as like understanding where these numbers come from. And the actual boosting process is the exact same process we're using. It's just you do this 1,000 times. And rather than using 30%, you use something like 1%, okay? And that ends up creating a model that has pretty good performance. This is, again, doing a terrible job of fitting the data, but that's what we have there. Okay, and that's it. That's all I have here. So we'll I guess wrap things up here. Thanks for a great quarter, and good luck as you guys study for your final exam. And so I guess see you on Monday, and that will be it. Have a great summer. Are any of you guys graduating? Okay, well, congratulations. Unfortunately, I had already made travel plans, and then they announced that the graduation is going to be held on Monday. So I will not attend graduation. I'm really sad about that. But congratulations. So yeah, wherever you guys end up, I wish you guys the best. If we're not connected on LinkedIn, go ahead and send me an invite, and I'll add you. I always enjoy seeing where some of my former students end up. It's always exciting when it's like so and so started a new job as like director of director of data science at someone's someplace, and it's like, oh, good for you, right? It always feels encouraging. I don't know, I always like to think like I played a small role in their education and preparation. So yeah, thank you, everybody. You don't have to do that. Thanks.